Presented by Santhan sir. He is a principal engineer at Intel. His work involves HPC, specializing scalable interconnect fabrics, MPI, PGAS, and open fabrics interface. Before joining Intel, Dr. Sir was a research scientist at OSU, and he also held a postdoctoral position at IBM, T.J. Watson Research Center. He has published more than 20 papers in major conferences and journals related to these research areas. He graduated from OSU in 2007. So today he will be talking about implementing high-performance MPI over oneAPI level 0. So Santhan, please share your slides and you can get started.
Hey, can you hear me?
Yes, yes.
Okay, so I'm going to start sharing the slides. Are the slides coming up?
Yes, yes, it is coming up. Yes. No, the previous one.
Can you see my video too?
Yeah, I can see, but the slides currently the outline slides are showing on the left.
Okay, so let's try to do the full screen. Is that working?
Yes, yes, this is great. Thanks.
Okay. Hey, thanks for having me, Dr. Panda. Good to be back, but it's not really the same without being in person and having been to I think all but the one mug. I feel like it's like a yearly tradition for me now. I think only Adam Moody has been to all the mugs that in addition to me, but I don't know if any other folks have that record yet, but it's definitely weird not being in person, but still happy to be here. So today I'm going to talk about how you implement MPI over the oneAPI level 0 interface. And my talk is going to be a little bit different than the talks that have preceded me. My talk is really aimed towards a lot of the programming aspects of it, which I know that in Dr. Panda's lab we have a bunch of students who watch this, and since oneAPI level 0 is new, I thought like maybe we should do a more programming oriented talk. So let's get into the talk. So as we've seen that the type of demands from the applications have really diversified. In the past, we had scalar, a little bit of vector, but then with the advent of the deep learning type of workloads, now you have the matrix workloads, which with the tensors, and also for the spatial workloads have also starting to emerge. There was discussion about DPU and data parallel access, which is in some respects just spatial programming, right? What we saw is that there's no real common language or APIs to actually unify all of them. So the programmer has to jump from one environment to completely another environment. If you write your code on CPU, it's different. If you run on GPU, it's very different. So this oneAPI stack has been envisioned from a top-down fashion, and the specs are now available online on oneapi.com. It's based on industry standards and open specifications, and mostly interoperable with the HPC programmers. So let's look at the bottommost layer of level 0 of oneAPI. So this is called level 0, right? And the goal and the motivation for this API was to simply expose all the device capabilities to a set of high-level languages or libraries, and give more control and low-level access to all the device feature sets than typically we're done with the OpenCL stack, and really focus on getting the software out of the way when it comes to interacting with your accelerator devices. and also support many core threaded applications where you can have multiple threads accessing the same devices. It also brings some modern language features like function pointers, unified memory, and so on. And from the API point of view, this is the typical thing that the MPI library will have to deal with. It's just devices, memory, peer-to-peer access. I'm sure you guys are already a lot familiar in terms of the concepts. And then for the tools, we have the metrics and the profiling tools, debugging tools, and system management tools. So looking at mainly the MPI requirements, I want to look at the very top level requirements. So how do you get the devices? How do you select a device? If somebody launches a job on the node, how many, how you divide the GPUs between the ranks and selecting and so on. And then how do you do inter-node communication, say with RDMA? And then how do you do intra-node communication for accelerator to accelerator communication within a node? Like how do you copy across address spaces? Let's look at the level 0 device model, right? So every device is exposed by level 0 is actually a physical device in the system. You can get all the APIs in level 0 are start with ZE. It starts with level 0. So you could do a level 0 device kit to see your enumerated set of devices. And each device can actually have a partition. And within the partition, you could have different sub-devices which may be interconnected, which are interconnected in all-to-all fashion. And then you can see, you can get sub-devices to get a list of sub-devices in there. And these sub-devices basically, whatever handle you get is just the device, is just the device list. So which means that you can use sub-devices the same way as you can for the main devices. And why you want to use sub-devices is if you want to have, as the picture shows, if you have NUMA awareness within a device, like multiple tiles within a device, or whatever organization a particular vendor has done inside the device, you could have applications target this NUMA awareness. Say you want to run one MPI rank per sub-device. And then the memory allocation within the sub-device can actually always be used by the device, by the parent device. Then, if you look at the device assignment requirements, so you have two main problems. Like, how do you have all the libraries within a process see the same device and the sub-device? So some user obtains some memory from oneAPI or data files, C++, which is a part of oneAPI. And it uses MPI to basically transfer the data. Are you seeing the same device within the MPI layer or not, right? And then if you want to partition the devices between the ranks on the node, then basically how do you do it? Like, can you give device 0 to rank 0, device 1 to rank 1? For 4 MPI ranks on one device, can you divide the sub-devices amongst the ranks and so on? So to control this, one of the knobs we have is called the ZE, affinity mask environment variable, which assigns devices to a particular process. So the first call in level 0, which is the ZE init call, will read this environment variable mask if it is set. And any further calls for device get basically obey this mask. So and on the right, I'm showing an example of a process that is spawned with affinity mask equal to 1.1 and 1.2. Basically, what this does is tells the level 0 layer that when the user asks you for an enumerated list of devices, we have device 1 is reported as device 0, right? This is the 1.1 part, and the subdevice 0 is actually what is physically 1.1, and logically 1.2 is the same as subdevice 1. So it allows you to basically constrain in any arbitrary fashion the list of devices and subdevices that are seen by a process. And this you can, I've just picked one example, but if you go to the oneAPI.com website, and you can see we have several other examples listed there. And then, like, how do you assign devices to the ranks? So we have two approaches. One is the MPI the MPI library and runtime are intelligent, and they want to do like a NUMA node aware placement. So whenever the MPI process launch, you could use any OS specific techniques to find the PCI hierarchy. You see which accelerator is close to which process, or you could use middleware like hardware lock to get the same information in a useful, simple manner, and then partition it. And you could also use level 0 to get the PCI device IDs assigned to the particular devices if you want to operate with the device handles. This is a sysman is a different set of API within the within the level 0. We have the core compute API and the system management API. That's what it stands for. And then you can have distribute the devices for the like the user specific configuration. This is really just left to the MPI implementer. Like typically for multi-NIC, we have round robin, block, all kinds of things. So depends upon the MPI implementation to offer its users various options. So here I've shown one example where you have dual MPI exec of 2 ranks on the local host, and the MPI library is able to set ZE affinity mass equals 0 on rank 0, and it will use device 0, and affinity mass 1 on rank 1, and it will use device 1. So let's look at the internode peer-to-peer communication, and an example of usage is the RDMA over the NICs. So the RDMA access is built around the DMA buff mechanism, and I don't know how many of you were attending the OFA talks this year. Genshin from Intel, he covered some recent work that he has posted on the Linux RDMA website mailing list about how to get DMA buff peer-to-peer mappings working between the NIC driver and the GPU drivers. So this is exposed via level 0 for things like MPI, and here I'm just showing the MPI aspect of it. So as you might have heard, that the DMA buff is a standard mechanism that's already in the kernel for peer-to-peer sharing, and it's exposed by a file descriptor that an exporting driver basically creates a file descriptor, and that file descriptor can be passed to any other importing driver, and using the mechanisms that are defined there, you actually can get a list of DMA addresses. So what we're showing here is this file descriptor is basically the ZE mem get IPC handle call, who returns you a file descriptor that you can pass around to. Here in the example, a GPU driver is exposing the file descriptor, which is passed on to the NIC driver, and the NIC driver can use it to obtain the DMA address. Then another common problem that comes to MPI implementation is that when the MPI user calls MPI send, it doesn't really say where the buffer is. Is it on CPU memory or is it in device memory? So MPI library has to find this out dynamically. So we have a call for memory get alloc properties where you can pass in the context and the pointer of the send buffer, and then you get back a property structure and the device pointer to see which device and what are the properties of the allocation. So the property ID, a thing to note for MPI implementers is that typically we implement a cache over this so that you don't have to repeatedly call these functions. The environment team is very well familiar with this technique. And this property ID will change if the virtual address has been reassigned to a different physical address. And it can be used for the MPI registration caching. And the device on output will say which device the buffer is on. So if you want to optimize something in the library, you can. And if it was not, if this pointer was not allocated through level 0, then it'll just say memory type unknown. You got to go figure out where this memory came from. So on the right, I've just shown some of the structures to see. You can also know other things like page sizes, whether it's a device allocation, shared allocation, and so on. Okay, here's just a quick sample of the point-to-point pseudocode where I'm just showing an MPI send call. As I said, first you need to do the get alloc properties to see where it was allocated from, and if it is, say, of type device property, I want to do an RDMA with it, then get the base address, and then once you get the base address, you can check your MPI registration cache to see whether you have registered it before. Typically, if you had a NIC registration as well, this will be present as part of the cache entry. If it is present and this is actually the same ID as you got before, then you can go ahead and basically just send it. Here in the example, I'm just using LibFabric, but it can be anything really that supports DMA buff. And then if it is not present in your cache, then of course you need to get the IPC handle, and then you need to pass the IPC handle to the network library. Here it's just shown example with LibFabric. FIMR regadder can take this FD and pass it to the appropriate NIC driver through its provided layer, and then you can put it back into your registration cache for the next access. And as we know, HPC applications typically reuse buffers quite a bit, so this is fairly effective. Okay. So let's move on to the next requirement, which is intra-node peer-to-peer communication, which is communicating between address spaces of two different processes, and this can be within a device or across links or so on. So when you look at these peer devices, you can establish whether or not you can access peer devices based on multiple ways. One is the main compute API of level 0. This is appropriate to use in the main library, which is level 0 can access peer. So you can just open the device and pass it the device peer device handle and see if this is actually accessible. And then if it is true, then if the device is if the two devices are the same, obviously you can true, or if it is connected via some scale-up fabric or they're under the same PCI root complex. Like alternately, there's another API we call the Sysman API that I introduced before. You can use some tools, diagnostics, or if you have some advanced MPI library, also can use this. And with this, you can basically, with the device handle, you can walk through the API, and you can figure out, what is your port ID, what are your speeds, is the status active, inactive, the typical things you could do with your InfiniBand stack that this community is very familiar with. Similar type of things are available over there, and you can do. You can also see if this port is connected to a remote port ID. You can also get this information locally. So you could construct your own topology map of how things are connected, how devices are connected. And then based on that, you can do collective optimization and communicator localities, specialization, whatever you want to do. Okay, so the basic IPC technique is a memory copy where we basically enable mapping of the VA from one process, process A in the picture. You can create an IPC handle, and you can pass that IPC handle to another process B, where you can establish these memory mappings. And then process B can just do load store DMA to this mapped address. And as I mentioned before, ZE get IPC handle, which creates the IPC handle on the exporting process. And on the importing process, you basically do an open IPC mem handle. And the IPC and this IPC handle is just an FD of type DMA buff. So as I mentioned in my scale out NIC communication set of slides before, this is basically the same handle. It's the same type of, so from the exporting driver point of view, it is just DMA buff. Whether you want to hand it to a driver in the same process or a different process, it doesn't really care. And then if you pass it to the other process, and then you can use the open mem IPC handle there to get essentially a list of DMA addresses on the other process. So I didn't really go into a lot of detail about level 0. There's a pretty big spec with a lot of use cases. I just want to very briefly touch on fences and events and command queues and various synchronization mechanisms, because these really belong inside the MPI library. So what I'm showing here on the code example is that you can create a fence, and a fence is basically you can once you have a command list, you can basically wait on the entire set of commands to be complete, and then it basically signals a fence. Like in the ZE command queue execute command list, you can pass in the fence. And then if you want to wait on individual memory copies, then you can use this event structure, and then you can pass on individual memory copies, like shown in the command list append memory copy function. You can have a memory copy start when you have a signaling event, and then once it's done, it can also raise an event. And then a couple of other things, like this command list is executed in the first in first out manner, but completion of the commands in this list is out of order. And this either if you're dependent upon the operations to complete, then you can do basically a fence, or you can have individual completions via events. And if you just if you want the host to wait for everything to drain, then you can do a fence host synchronized. One more thing I want to say is, like, if you want to use the DMA engine underneath level 0, then when you create this command list, you can pass in a hint called copy only. So then that will let the implementation choose the right type of engine to move the data for you. And really, these are several chapters in the level 0 spec. So I'm sure I'm not doing it justice, but I just wanted to give a flavor of the things that are required. Okay, so I want to show a sample intranode protocol. Here, the MPI rank 0 is trying to send a message to MPI rank 1. So you do a send, and I'm showing the standard rendezvous flow, and obviously eager optimizations and various optimizations are possible on top of this. So you send the ready to send and the tag and so on, and then on the remote side you can do a match, can get the IPC handle, and you can allocate an IPC event from an event pool, IP event pool, and pass along the buffer's IPC handle and also the event index in the IPC event pool onto the sender, and then the sender can open the buffer's IPC IPC handle, and you can do a memory copy. And then when this memory copy finishes, it basically writes the event that the receiver allocated before. And once the event is signaled, you can either pass a message or whatever way you want to basically want to tell the sender that you're done, and then you can close the IPC handle. Of course, if you have a cache, you wouldn't close this IPC handle until this buffer was being freed at the receiver. And the thing to note here, this is different from other implementations, is that the IPC handle is, as I described, is just a DMA bus, file descriptor. And normally you can't just pass file descriptors from one process to another process. That's a standard Unix mechanism. So the file descriptor needs to be passed with a defined mechanism called FT passing in the kernel. So if you want to look at how this is done, I've included a link to the man page, and look at the SCM rights flag in that page. And so that's pretty much all I had. Just to summarize, level spec is open. I've put the links here. It already has all the building blocks that you need for MPI, and the RDMA operations with the lib fabric, verbs, etc. is under progress. It's been talked about in the Linux RDMA lists, and the open source MPI implementations are just starting now. NPitch work is ongoing, and they already ported the MPL layer to level 0, and the rest will be coming soon. And hopefully we can get several MPI stacks enabled with level 0 in addition to NPitch. So that's it for me.
Yeah, Santhan, thanks. So there is one question on the QA box. So if you open up. Just go to the Q&A. Just go to the Q&A on the Zoom.
Yeah. Okay. Pasha asks, is ZE mem galloc get alloc properties a system call? I think the level 0 spec doesn't define whether it's a system call or not, but I think I would expect it to be user mode, but if it can do some simple address string checks, but it could be a system call, so it's better to avoid it with your registration caches.
Okay. Are there any other questions from the audience?